Good morning, students. Sorry I won't be with you today. My child's daycare ended up closing, and I may miss another day this week. But what I like to do is go over a couple warm-up problems. So go ahead and hit pause, try these problems, and then we're going to go over them when you're done. Okay, so finding the general solution. You have to pay really careful attention to the directions that they have. So this is the one where we have to find the plus c. All right, so what I'm going to do first is I'm going to officially, we don't really technically multiply it over, but we have to move the dx over to the other side. And what that does is the dx has to be with the variables that it's kind of, that are alike. So what I'll do is I'm going to rewrite this first as dy equals cosine of x. And then instead of x to the negative 1, I want to think of that as 1 over x. And then we've got 5x to the fourth, and we're officially taking dx of this entire side. Now, our job is to find the general solution, which is the antiderivative. And we introduced that little squiggle symbol called the integral. We're going to be making connections all day today with how and why we use this and what it means. But remember, you can always sneak a 1 here. So I want to find the antiderivative of 1 with respect to y. So whose derivative gives me 1? It's y. And then I'm going along the line. Now I'm doing it with respect to x. So whose derivative gives me cosine? That's sine of x. Whose derivative gives me 1 over x? That is the natural log of x. And we put the absolute values there. We'll talk about that a little bit later in this idea. As we start developing more antiderivatives. But the power rule, here's how I like to think of the power rule. If we were taking the derivative, we would always take 1 away. Well, we're taking the antiderivative, so we're actually adding 1 up top. So if I have a 1 up top, if I add 1 up top, that puts a 5. Now, a lot of kids kind of get confused with, and I'm going to put this 5, so 4 plus 1 is 5. And here's the way I like to think of it. We originally had a 5 there. If I put a 5 up here, then I have to compensate for that 5 being present when I take the derivative. So I'm going to actually put a 5 underneath it, which reduces these out. So then whose derivative gives me 5x to the fourth? It's originally just x to the fifth. And then the last part, we always add the plus c when we do a general solution. Now, the last thing you could do is you could clean this up a little bit just by saying the 5's reduce out. And if they ever ask you to verify your solution, what you can do is if you take the derivative of each one of these pieces, you should get right back to where you started. Okay? All right, so that's the first one. The second warm-up was just a quick review of the midpoint. So this is the trapezoidal sum, or I'm sorry, not trapezoid, midpoint, so rectangle Riemann sum, and we're looking to use the middle point. Now, when we look at this, the interval here, the lower bottom of the interval is where we start, and the upper limit is where it ends. And then they want us to do 4 subintervals indicated by the table. Well, 4 of them, if you notice, if I connect and make the rectangles, if I did 1 between each pair of input-outputs, there'd be 8 of them. Well, I need 4, right? So 4 subintervals, that's the same thing as rectangles. So I need to create 4 rectangles. There's 1. Now notice, I start at 1 and I go to 3, and then the next one goes from 3 to 5, 5 to 7, 7 to 9. But since we're using the midpoint one instead of the right or left, I want to take the value that's in the middle, which is right here at 2, 4, 6, and 8. So those are the values that we're looking at. And now we're going to set up the interval from 1 to 9 of f of x dx. Now I'm going to put a estimate or an approximate symbol here because this isn't a perfect area under the curve, it's just an estimate. That's what the LRAM, RRAM, and midpoint Riemann sum approximates. So what do? I need the distance of this rectangle, the width, and that's from 1 to 3. So that width is 2. So I'm going to put that first, and then we multiply by the height of the rectangle, and the height is how tall is this rectangle going to be? Well, that's indicated by the output of the midpoint range. So that output is 10. Now, you shouldn't always just assume that it's going to be the same width every time, because sometimes it's not. So I'm looking at the distance between 5 and 3 is 2. So that width is the same. And then the height is how tall is it at 4. Well, the height is the y value going up, so this value would be 7. And that would be the area of this rectangle. And then we got to find the area of the other two. And you don't technically need to show any work up here if you can do it all in your head, but from 7 to 5, that area or that width is 2. And then the height is the output at the midpoint value, which is 14. All right, and then the last one, from 9 to 7, its width is 2. And then the height on this one is 17.5. Okay, so now I'm just going to go ahead and find the sum of each one of those pieces. And what is that? 24, 25, 35. And then add them all up. And we get a total sum or approximation at 97. And this would be the midpoint approximation method. Okay. Now notice really quick, what would change if I asked you to do the LRAM? Right? If I said do the left-handed side, not much would change. Left-handed side would be using this endpoint. So I would do 2 times 11. And then if I did left-handed, I would use this output for the height. So this would change to a 3. Here we would go to an 11 for this one, and then 17 for this one. And notice how we ignore the end one when we're doing the left one. So the this would be very quick. If I wanted to do the left approximation method, I would just replace all the red values with the green values, and that would be the LRAM. Okay, so what if I wanted to do the RRAM? Right? What would RRAM be? Well, RRAM would be using the right values, so I'd do the 3, the 11, the 17, and the 18, and notice I would ignore the first value if I'm doing the right approximation methods. And then I could just plug in the purple ones here, so 3, 11, 17, 18, and then add them all up. So that's just a quick review of LRAM, RRAM, and MRAM. All right, so today we're actually going to split this video up into 2 parts. The first one is a review of antiderivatives, and then the second video is going to be about trapezoidal approximation methods, which we haven't done yet, and something about an over and under estimate. Okay, so don't write this, but we're going to think of basic antiderivatives. What is an antiderivative? Think of it as reversing the derivative, or I like to say in my head, whose derivative gives me this? So if this is my derivative, I want to find the antiderivative of this function. Now you could do all the work. You could move the dx over to the other side and then find the antiderivative. So I'd get y, and then whose derivative gives me 100? It's 100x plus c. That would be the antiderivative. Okay, well, notice I'm trying to give you different rates. So whatever rate is on the bottom will move over, and this variable should always match with this variable. So I get ds equals 14f df dt when I move the df dt over here. And then we are going to take the antiderivative. So there's always a 1 here, so I'm thinking whose derivative gives me 1 ds, that's s. And whose derivative gives me 14f? Well, technically there's a 1 here already, so I'm going to add 1 up top. So I'll get an f squared. And then notice, if I put a 2 up top, I should put a 2 on bottom. So I left the 14 there. And then that would simplify to s equals 7f squared plus c. The best part about these types of problems is you should always be able to take the derivative of this side and it should turn into this, right? What's the derivative of 7f squared? 2 comes down and we take 1 away. I get 14f. The plus c is always there because of the constant. We talked about that last week. All right, let's try a couple of these power rules. So here's what I like to do. You don't really need to rewrite that. You put the dt over on this side. And then we just take the antiderivative. Well, let's deal with this one first. If I have a 5, I'm going to add 1. So this becomes t to the 6. If I put a 6 up there, I have to compensate for what that would be. So when the 6 comes down, it gets eliminated. So I'm going to put the reciprocal here. I'm going to divide by 6. So like here, I've got a 2 up top. I'm going to add 1. And that becomes t to the 3rd. So if I put a 3 up here, I'm going to divide by 3 or times by a 3rd. Now, if it's already a t, there's a 1 there already, so then I'm going to add 1. So this becomes t squared. And then if I put a 2 up there, I got to compensate for that and put a 1/2 out in front. Okay? And then if it's just a 3, this will be 3t plus c. And I forgot to do this side. This was just a 1, so that's going to be s. And there's my answer. Okay. If you're not sure, take the derivative of each piece and you'll see how the 1/6 and the 6th reduce out and you're left with just t to the 5th. Okay. Then they can get a little more tricky. And this is kind of the thing that students really struggle with here. So what I'm going to do first is move the dx over. I give myself a little bit of room here to write. And then I'm going to take the antiderivatives of each side. So it's technically a 1 here. The antiderivative of 1 dc is c. Now what would happen here? I have to add 1 up top. So watch what happens. I'm going to add 1, but it's going to be a creative form of 1. 7 over 7 is still 1, but I did that so I can add my like terms. All right, so now 4 plus 7 is 11 sevenths. But if I put 11 sevenths up here, I've got to times or divide by 11 sevenths, which is timesing by the reciprocal. Okay? If you're not sure how that works, stop right now and take the derivative of this. You'll see the 11 sevenths come down and it reduces with the 7 elevenths. And then I take 1 away and I would get back the original value what I had before. Okay? E to the x is really friendly, especially if there's nothing up here. So this is just e to the x, and the antiderivative of e to the x is e to the x. There we go. Okay. If you are not super comfortable with all your derivatives, all we're doing is reversing the derivative concept here today. So if you look at page 372 in your textbook, they say if this is your function, here's the antiderivative, right? Whose derivative gives me 0? Well, it's a constant. Whose derivative gives me 1? It's x plus c. So another way to think of it is if you have the antiderivative, if you take the derivative of this, you should get a function right here. And we'll talk a little bit more on Thursday, Friday about lowercase f and capital F. But this is a list of the antiderivatives in case you haven't memorized your derivatives and you're struggling to go backwards. Okay, some of these are trickier. And like I said, we'll go over them when they come up, especially ones like sine inverse. Okay, so check out that page in your textbook. Go ahead and pause the video, and I'd like you to try these 2 problems right now. Okay, we're going to go over them quickly. Now notice the notation here. It doesn't say dy dx. It just says f, which is fine. We just want to find the antiderivative of each side, and you can always put a dx here, or you can just say, you know what, this will be a capital F, and then I'm thinking whose derivative gives me e to the x. Well, that's just e to the x, because the derivative of e to the x is e to the x. This one's tricky. So I'm going to do a little side work on this one, just so you can kind of see how this value goes. The first thing I would do is I don't like the way it's written, right? I'm not going to do any I'm not going to do any calculus right now. I'm just going to rewrite this algebraically. And now it's a power rule. So if I'm taking the antiderivative, I'm going to add 1. So then this becomes x to the negative 1, right? Negative 2 plus 1 is negative 1. And that 6 is going to stay there. I'm just going to leave the 6. However, if I write a negative 1 up top, I have to divide by negative 1. And then watch what happens when I simplify. I end up with negative 6x to the negative 1. And that is the antiderivative, or you could rewrite it this way if you wanted to. Okay. And then the last one, whose derivative gives me negative sign? That's a positive cosine. And then we always put a plus c at the end because we're doing antiderivatives. Okay. And then we have this one right here, find the particular solution. So we talked about this the other day. You're supposed to watch the video that Mr. Waffler did last Wednesday, and he talked about finding particular solutions. It's the same work we just did, right? So you're going to find the antiderivative. So what I would do is I'd move this dr over to this side, and then we're going to take the antiderivative of each piece, knowing that there's a 1 here. So this will be a v, right? Antiderivative of 1 with respect to v is v. Now here's a little bit of a tricky one, and we're going to give a different method in about a week that makes this a little easier. But notice, if it's e to the x or anything else, it's going to be e to the 4r. But if I take the derivative of that, a 4 would come down here. So I'm going to compensate for the fact that there's a 4 there that would come down. I'm going to put a 1/4 out in front. If you're not sure, take the derivative of this piece and you'll see how the 4 cancels out with the 1/4 as you do the chain rule to get back to where we started. All right, with this piece, I'm going to add 1 up top. So then I would get r to the 4th power. But if I put a 4 up top, I'm going to have to divide by 4. And that 2 was originally there. So that'll reduce down to 1/2. And then whose derivative gives me negative sign? That's a positive cosine of r plus c. So there's my general solution. Well, what's the difference between a general solution? I'm going to call this GE or GS for general solution. Well, now they give me an R value and a V value, right? Another way to write this point, if you aren't comfortable with function notation, is RV. So I'm going to plug in those points to try to figure out what is this C value right here. That's our goal. And that's what a particular solution does, is it just means find the C value with the point that is given. A lot of times they call that the initial condition. So I know that V is 4. I know that E is 0. And I'm just going to reduce this down to 1/2. Oh, I'm sorry, I think I said E is 0. R is 0. Put a 0 for R. And then solve, simplify. Right? The thing you have to remember, this will be e to the 0, which is 1, and 1 times 1/4. This will be 0. I don't have to write that. Cosine of 0 is 1 plus c. And then I know at some point, notice here, we've got fractions. So I'm going to turn these all into the same fraction. So I'm going to make that 4/4. I'm going to make this 16/4. Right? And then 1/4 plus 4/4 is 5/4. And then if I subtract 5/4, I get 9/4. No, I'm sorry, 11/4. Right? 5 minus 16 is 11/4. Now there's the C value. So what do? The particular solution is we found the value of C. So all you do is go and rewrite it. B is equal to 1/4 E to the 4r plus 1/2 r to the 4th plus cosine r plus 11/4. That is the particular solution. Okay, so it's particular because it's specifically for this given point. All right, so last one here. What about motion? Right? We've talked about motion. We know the derivative of the position gives me velocity. The derivative of velocity gives me acceleration. So what if, and this one you can do together, but find the position function, s of t, of an object at time t if its acceleration is 8t minus 3. And then the initial conditions for velocity are 0, 4. And the initial condition for position is 0, 1. So what I need to do is I need to take the antiderivative of this function. So you can kind of think of it two ways, and it's with respect to time. Now, when I take the antiderivative of acceleration, what do I get? Velocity. Right? So then I'm just doing the power rule. There's technically a 1 here. I'm going to add 1 up top. Now, if I put a 2 here, I'm going to have to divide this by 2. So some people can put it here, and then they just write, well, 8 divided by 2 is 4. Some people like to write 8 divided by 2, however you want to think of it. And then this is a constant. The antiderivative of a constant had to have a variable at one point. So now I have to put plus c, right? Now this isn't position. I got to find the position, but before I can find the position, I need to use the point 0, 4. When time is 4, velocity is 4. When time is 0, velocity is 4. So if I plug in a 0 here, and a 0 here, and a 0 here, well, v of 0 is 4, right? That's what v of 0 is equal to. And if I plug in a 0 here, and a 0 here, what's left over? 0, 0, 4 is equal to c. So this is like the particular solution that we just did, and it's going to go right there. So then I just want to kind of rewrite this one and say, all right, well, here's velocity. This is the equation that will give me velocity. But we know that c is 4. So now, if I do the exact same thing, the antiderivative of velocity will give me position. So we can go ahead and take the antiderivative of both sides. And notice when I say antiderivative, I'm putting the integral symbol with respect to time, because all of these have an independent variable of time. So the antiderivative of velocity is position, which we called s of t. They named it right here. And then we're just going to undo the power rule again. So I'll use a separate color for this one. So if I have 4t squared, I'm going to add 1 up top. So that'll be a 3. Now notice that 4 is not going to be reduced out. If I put a 3 up top, I have to put a 3 on bottom. So that's just a 4/3. And this already has a 1 here, so I'm going to add 1, and that'll be t squared, and then negative 3 divided by 2. If I put a 2 up top, I have to put a 2 down on the bottom, and that doesn't reduce, so I leave it. And then whose derivative gives me 4? That's 4t plus c. Now notice, anytime we take the antiderivative, you have to have a c there. Now some people like to put c1 here, because this c is officially for velocity, and you can put a c2 here, and that just means that this one's specific to position, which means now I got to go back and do the same work when t is 0, s of t is 1. So if I plug in 0 here, s of 0 is 1. If I plug in 0 to all of these spots, notice this will be 0, this will be 0, this will be 0. The only thing that's left over is c is 1. And then I just go right back to that spot, and I can write the position equation. So s of t is equal to 4/3 t to the third minus 3/2 t squared plus 4t plus 1. Now, if you're not certain on this, what you can do is take the derivative of this. If you take the derivative of this, you should get back to velocity. Take the derivative of velocity, you'll get back to acceleration. And that's all we're doing. That's the antiderivative. All right, the next video is going to talk about trapezoidal methods, but I'm just going to pause here and let you guys get a little breather. So watch the next video.